Hello, let's continue with our examples of Lesson 6, Hydraulics of Networks. We pretty much examined this three-well system, this three-reservoir system, and now I want to look at a loop system. And this is where pipes rejoin at a different node. Key things are nodes have continuity and energy, and the links have head loss along the flow line. Skip through all this because we've done it already, and let's start here. So what I'm going to do is I'm going to deviate from the PowerPoint slides because the PowerPoint slide uses an older solution technique, and we'll actually use the solution technique we just developed and actually adapt the spreadsheet we just developed for this next problem. So I want you to take a look at this, and then we're going to go ahead and draw the problem on paper, formulate the necessary equations, build the Jacobian, and run the solver. So here's the problem. We have this setup, and it's drawn better obviously in the PowerPoint. This is a 3,000 foot pipeline. That's a 3,000 foot pipeline. This one's 2 foot diameter. This one's 1 foot diameter. I'm going to call this node A and this node B. Node B, there is 20 cubic feet per second demand. And node A, there has to be a matching amount, but we're going to treat node A slightly differently. We're going to treat node A as if it is a fixed grade node, and I'm going to go ahead and set the grade at 100 feet. We could set the grade to anything we choose, but I'm going to choose 100 feet. And this will call pipeline number 1. This will be pipe number 2, and the flow directions are indicated by the purple arrows. Okay, the problem statement in the example is friction factor 0.01, but we're going to go ahead and just use the pipe roughness. Since we've just built the ability to handle that, we might as well just use it. So we'll make them iron pipes. We'll use a roughness height of 0.00 0.03 feet. Actually, we'll go look these up. So I'm going to cross that out. I'll look that up when I need it. Okay, so using our same model, we're going to have flow in pipe 1, flow in pipe 2. There's a value of head at known B that's unknown. There's our unknown vector x, and there's a right-hand side. We're going to have a node balance equation, pipe 1 loss equation, and a pipe 2 loss equation. So for the pipe 1 balance, we have pipe 1 comes into node B, pipe 2 comes into node B isn't part of node B, and the right-hand side is 20, and that's the demand. For pipe number 1, let's look at pipe 1, and then we'll pick up the pattern. We have the head at A minus whatever the loss in 1 times Q in 1 is, equals the head at B. This is our unknown. This is known. Let's rearrange. So we have minus L1 Q1 minus HB equals minus HA, and we now have the pattern. So this is minus L1, 0, minus 1, minus 100, 0, minus L2, minus 1, minus 100, and finally the unknown vector will be the flow in pipe 1, the flow in pipe 2, and the head at node B. That's really all we need to do to be able to go to our spreadsheet. So let me leave that aside, and we'll bring up the spreadsheet. So here's the spreadsheet, and all I did was take our 3-reservoir 1 and literally copied it and have renamed it. This will be renamed for the loop sheet. Now, we now have 3 equations and 3 unknowns instead of 4. Let's go ahead and label our pipes. We have pipe 1, pipe 2, and we have node B. So all the pipe information is going to go away. The matrices are going to change size. So we'll clear out as much of the node B info as we can. We have to have an initial head at node B. Let's make it 100. Initial flow in pipe A, 1 and 1. Now we'll go ahead and parameterize it. Pipe 1 is 3,000 feet long. Pipe 2 is 3,000 feet long. Diameter is 1 feet and 2 feet. For roughness, we don't know what it is yet. We'll look it up. We'll leave it at 0.0026. We're in different gravitational units. The viscosity, been using it a lot, so that should be pretty close. That's probably at 50 degrees Celsius. Pi squared doesn't change. Diameter to the 5th power. To the 5th is 32. That makes sense. Okay. That doesn't matter, so now we have to modify the node arc matrix. So this is going to break a lot of things. We're going to get errors, and we're not going to sweat it. P1, P2, node B, node B, P1, P2. This stuff is all gone. We'll take this out. That's now empty. That's empty. Let's see what we can do to clear this one. I actually want to, I'm going to leave it because it'll be handy to modify it. All right, let's clear some of the formatting. Okay, I'll fat border all that. I will clear formatting. Clear formatting. Actually, I think I can probably, yeah. All right, that's about what I have to work with. Everything's resized, and so we will continue from there. Let's see if it'll allow me to do this. I hope so. Cool. Sometimes that doesn't work. All right, let's make our node arc incidence matrix. So we've just done that. It's 1, 1, 0. This one is going to be minus L1, 0, minus 1. This one's going to be 0, minus L2, minus 1. Our right-hand side is going to be 20 for the demand, minus 100, minus 100. Our x will equal transpose SPOSE of our current vector. Our f of x is going to be equal matrix multiply that times that minus that. See if that makes sense. I'll buy that for $1. Okay, now we have to build our Jacobian vector. See, recolor everything. That one I think I used yellow. This one I think I used yellow. The coloring is for us. This one has normal. This one has normal. All right, we're pretty close to having everything ready to go. We'll resize the matrix. Resize that. Oh, it's being a snot. And this one's going to have to be that. All right, I'm going to try to set up and do this again. Okay, so this is equal to mmult of -1 times the inverse of the Jacobian multiplied by right-hand side produced values. This one is equal to that plus delta x. This is equal to transpose of that. See if everything seems to make sense. I think so. Our friction factors are a bit high because that roughness is a bit high. So let's go look up the pipe roughness. I don't know, let's make them steel pipes. Pipe roughness. Roughness pipes. Be nice to have it in English units. There we go. So commercial steel is 150 times 10 to the minus 6 feet. Zero 0.00015, 0.00015, 0.00015. Our friction factor is seemingly still a bit high. My Reynolds number is kind of low. Well, let's go ahead and see what happens. Hit 1. We're going to do it one iteration at a time, so I'll change that back to 1. Choose OK. And I want to look at f of x and see if it's actually going. Cool. Gets to 0. The friction factor is quite a bit higher than in the problem statement. I believe it said it was 0.01. We could override that by, let's smooth out our pipes just a wee bit. Our friction factor isn't getting smooth no matter what we do. Reynolds number V D over viscosity. And my Reynolds number, this isn't that far away from laminar. Just for grins, let me add a row. I'm going to fix it to the desired value that was in my example that's on the deal, and then all we have to do is move to that. I want to run it on the fixed friction factor. I actually don't think it's going to make a whole lot of difference. There we go. So using the fixed friction factor, it says the flow in pipe 1 is 3 cubic feet a second, and the flow in pipe 2 is, let's call it 17 cubic feet per second. If we were to go back and look at the example worked the old way, we would come up with 3 cubic feet a second and 17 cubic feet a second. The old way states that the head loss is 6.79 meters, which doesn't fit the problem statement because the problem is in feet. But we've now seen how to deal with branched and looped systems. Let me go back and switch my thing back to the non-fixed friction factor. Okay, so with the friction factor quite a bit more variable, we have different answers, but they're roughly the same. We're looking at 3 and 17, which is what we had before. And pretty much the same results. So I'm positive that's working as best we can, and our computed friction factor is just quite a bit higher than was given in the example problem statement. All right, we're going to look at one more example. So the analysis technique we've just did is this one, the hybrid method. Let's consider this system, and we're going to take the same spreadsheet and modify it again. And the only difference now is we have quite a few more pipes. So let me copy that, and then we will So I'm writing down the particulars, 800.67. These are in feet. P3 is 700.67. P4 is 700.67. P5 is 800.67. And P6 is 600.5. We're given the sand roughness height 1e minus 5. And mu is 1.1 times 10 to the minus 5th feet squared per second. So if I move out to my overhead, I've just duplicated that thing, and now we were going to want to write our pipe and node equations. So we have pipe 1, pipe 2, pipe 3, pipe 4, pipe 5, pipe 6, and our unknown nodes are N1, N2, N3, N4. We'll have our X and we'll have our right hand side. So we're using the same thing as before, and then we'll have the node 1, node 2, node 3, node 4 equations, and then the P1, P2, P3, P4, P5, P6 head loss equations, and we're going to use that to construct a node arc incidence matrix. Now I'm going to cheat a little bit because I've done it already, and I may end up copying the node arc incidence matrix from the PowerPoint. Okay, so node number 1. Pipe 1 comes in, pipe 2 leaves, pipe 4 leaves, everything else is 0. Node number 2. Pipe 2 comes in, pipe 3 leaves, pipe 6 comes in, everything else is 0. Node number 3. Pipe 4 comes in, pipe 6 is leaving, pipe 5 is leaving, everything else is 0. And lastly, node number 4, 3 in, 5 in, everything else is 0. While we're here, let's get the demands. The demand at node 1 is 0. The demand at node 2 is 4. The demand at node 3 is 3. And the demand at node 4 is 1. Draw this line here. It's going to make it easier for me to keep track of what I'm doing. Okay, so now we have the pipe loss equations. And let's just look at pipe number 1. So pipe number 1, it has 100 minus loss 1 Q1 equals the head at node 1. Unknown, known, let's rearrange them. So I have minus L1 Q1 minus H1 equals minus 100. I've now picked up the pattern. So this is minus L1 minus 1 minus 100. Everything else is 0. Pipe number 2, I have minus L2. Pipe number 2 connects node 1 and node 2. So it would be head 1 minus L2 Q2 equals head 2. So it becomes head 1 minus L2 Q2 minus head 2 equals 0. So we have a plus head 1, a minus head 2, 0. Pipe 3, minus L3, 0, 0, 0. Pipe 3 connects node 2 and node 4. So it goes from node 2 to node 4, 0. Pipe 4. Pipe 4 connects node 1 and node 3. Pipe 5 connects node 3 connects node 3 and node 4. And lastly, pipe 6 connects node 3 and 2. So node 3, node 2. and my right hand side is going to be flow 1, flow 2, flow 3, flow 4, flow 5, flow 6. There's my system. Now we know the Jacobian of this thing is that thing, of this part is that part, Jacobian of 0 is 0, and the Jacobian of this is 2 times whatever it is. So now we have all the information we need to build our next model. This one's going to be a little bit more elaborate, so let's go ahead and edit, move a copy sheet, create a copy, choose the okie dokie, and we're going to call this, I don't know, the bridge system. Okay, so we have quite a bit of work to do because we have pipe 1, pipe 2, pipe 3, pipe 4, pipe 5, pipe 6, node 1, node 2, node 3, node 4. We'll go ahead and populate the pipe information, and then we will do the requisite linear algebra later. It's going to be quite a bit bigger, but it's the same methodology. Okay, that should, hopefully that'll keep it from protesting. So, pipe 1 is 800 feet long and 1 foot in diameter. Roughness, we're told, is 1e minus 5. Viscosity, we're told, is 1.1. And that's about all we have for now. Pipe number 2, 800, 0.67, 1e minus 5, 1.1e minus 5. These we can drag over because they're going to be constants. All that stuff is going to be constants. Let's get pipe 3. Pipe 3 is a 700, 0.67. Doing everything in feet. Pipe number 4, 700, 0.67. Pipe number 5, 800, 0.67. And pipe number 6 is 600, 0.5. Okay, we can make our initial flows 1, and we'll make our initial heads 100 everywhere. Let's see if I can get this part to work. $67. All right, cool. Looks like that's all built. Now we have the added fun of pretty much having to completely break this. Let's leave as much around so we have everything available to us. Copy that. Paste, that'll remind us how to build the node arc. And in 1, in 2, in 3, in 4, this will remind us of the equations. Let me just copy that, edit, paste a special, transpose it, picks up the pattern, cool. Okay, so that's all going to be green. This is all going to be what we're using, light yellow. These are all going to be old yellow, and that one stays blank. Let's clear out all these formats. All right, now we start entering the NodeArc instance matrix directly from our worksheet. 1, minus 1, 0, minus 1, okay, 0, minus 1, 0, 0, 0, 0, 0, 0. We're going to have x, which we don't know what it is, and we're going to have b. I don't want the green because it's not pretty. All right, let's go row number 2. 0, 1, minus 1, 0, 0, 1, 1, 2, 3, 4. There, quit doing that. Ha. Third node is 0, 0, 0, 1, minus 1, minus 1. Rest are zeros. We've already put them there. Fourth row is 0, 0, 1, 0, 1, 0. Rest are zeros. Let's reformat those. There we go. And now we need to put our loss terms. So this is minus that guy. Everything else is 0. And now we have to handle the head term. So this is minus 1, 0, 0, 0, minus 100, 1, minus 1, 0, 0, 1, 0, minus 1, 1, 0, minus 1, 0, 0, 0, 1, minus 1, and 0, minus 1, 1, 0. Those are zeros. I do not want that to be doing that stuff. Okay, so we'll finish the right-hand side. And these are going to be 0, 4, 3, 1, 0, 4, 3, 1. There's the f of x function, goes right there. All right, this equals transpose of our current guess function and this equals matrix multiply of that into the x function, and we subtract off b. Next, we need the Jacobian. So I think the easiest way to get the Jacobian is I'm going to copy that. Actually, I'm going to copy that. Do a paste and clobber. Jacobian, and I know that that equals that. This one equals 2 times above. And this one equals above. Jacobian's built. Now we need the dx vector and then the x k plus 1. Okay, so the dx vector, if you recall, is matrix multiplication minus 1 times matrix inverse of that guy multiplied by that guy, and then this is equal to that plus that. And finally, to get the update, I find it easy to have pull this guy down here. Do the transpose of the update. And what row is that? 52. So my update. Oh, cool. Did it really pick up 52? We lucked out on that. It must have captured the pattern when I moved everything. I believe we are ready to attempt to solve this problem. Get out. Here goes nothing. So we turn our iterator on, and we'll go over here, and we want to see f of x get driven to 0. There's something wrong right there. Because that value is not changing, so we have a sign error somewhere. But that was pretty quick. I'll go ahead and pause. I'm going to find the sign error. And okay, the error I found is I had not copied that all the way across. So let's reset it. Start it again. And we should watch this thing very quickly. Get to an answer. 0 to 8 places. Let's call that good. And so now our result is the flow in pipe 1 is 8. Direction is shown. Flow in pipe 2 is 3.8. Flow in pipe 3 is 0.27. Flow in pipe 4 is 4. Flow in pipe 5 is 0.72. Flow in pipe 6 is 0.37. And then the computed heads are as shown here, 0.56. And so on. Those friction factors are annoying me yet again. Reynolds numbers are off. So we still have another mistake. Let me pause and find it. Okay, the mistake is I had the viscosity wrong. Let it get its new answers. See, friction factors look about right. Reynolds numbers I can live with. I'm not happy with the head losses, but I'm going to have to accept them for the time being until I have a chance to investigate if those are indeed correct. Okay, I got to the bottom of this. I was calculating Reynolds numbers incorrectly. Now we're getting much more reasonable values, so we will run it one more time. It was incorrect in the other prior examples. I'm not going to go back and fix them. You can do that on your own. My issue was I was doing the velocity. Had the divide by 4 in the wrong place. So now we will run it out to its solution. Pretty much done. And when we now look at the results, we have 8, 3.89.27.4, 77 feet of head at node number 1, 41, 42, and 40 at nodes 2, 3, and 4, respectively. And that agrees reasonably well with the results that we would get using other tools. So I'm going to go ahead and save this and conclude this, and we now have the ability to handle some at least simple networks, no pumps yet, and we'll look at that in a future episode. Thanks for your attention. Bye.